Okay, here we go again. So I've erased the board with the exception of the final answer that we obtained for the part that was bending. Now I start from fresh. I start the problem fresh. So this is my 1 unit and this is going to be my P. Since we've already done it before, I'm not going to stop and repeat everything exactly the same. All I have to say is that if I start a coordinate here, x, that moves that way, then it's obvious that we've already shown that m1 here is equal to x, that v1 here is equal to 1, and that n1 here is equal to x. At the same time, we showed that mp here was equal to wx squared over 2, that vp was wx, and that np was 0. The issue becomes this bar. Well, not the issue, the point that I am making now is this bar. Before, we calculated the reactions and started bubbles from here. The question, the point I now make is, what if I don't want to do that? What if I just simply take this bubble to calculate what's going on in bar AB? So if I take that bubble, which is perfectly fine, because any bubble is perfectly fine, I see my 1 kip load here. The distance from here to here is still x. I don't need any new coordinate, right? And now I'm looking at the other side of the cut, right? When we looked from here, I was looking at the left side. Now I'm looking at the right side of the cut. So my notation for positive gets reversed from what we had before, right? So in this case, our notation for positive is, let's see, what did I say? Shear. Let me look at the previous one, make sure I don't change it around for you. Right, so we had N1 to be compression, that means that N1 is like this. We had V1 on that side going down, so we have V1 here like this. Well, actually, you know what? Now I'm thinking, why do I have to worry about that? I'm doing this problem fresh. But anyway, just to keep the same notation as before, M1 would be like that, V1 would be like that. And the moment M1 here would be like this. I don't really need to respect the previous because I'm just starting fresh. This is just the way I'm going to do the problem now. So that's my M1, N1, V1. So here, I can see that in this free body, some of the forces in Y requires that there be a 1 here, right? So that 1 has a component in the X and in the Y, and so we can see right away that N1 is equal to what? N1 is equal to 2 over square root of 5. V1 is equal to 1 over square root of 5. And M1 is X, right? So big moments about here. So in this view in which I did not compute the reactions and started this way, it's much easier for me to write the equations of statics because I don't even have to get this reaction start with this bar or anything like this. This is just another bubble a little bit further. The fact that the bar got inclined, who cares? Some of the forces in Y requires that there be a 1 here and a 0 here and a moment like this, and then the 1 gets decomposed into axial and shears as 2 square root of 5 and 1 square root of 5, right? And that's the end of that. Now the same thing happens when it comes down to the load case, in which case we are like this. So now this load here is 2WH, right? So that means that some of the forces in Y means that this is 2WH. There is no horizontal, and there is a moment here. Now how far is it from here to here? Well, this distance is still X, right? And this distance from here to here is H. Therefore, this is clearly X minus H. So this component here and this component here are going to be 2WH times 2 over square root of 5, and this is going to be WH over square root of 5, right? And summing moments about O, this MP is going to be minus MP plus 2WH times x minus h is equal to 0, right? Therefore, MP is equal to 2WH minus 2WH squared. So you can see that the statics became much faster, right? Let me see, I'm trying to stay organized here with the stuff that I have. Let's see. So this one is not needed. Now we have V is equal to WH over square root of 5. Okay. MP is equal to, why don't I have this stuff in the same place? Sorry, just triple checking, making sure I don't confuse the issue. Yeah. WH squared. No, this is Z again. I'm pretty sure that this is correct, but I just want to triple check so I don't have to go back and say sorry. So let's see. WHX minus 2WH squared, BP is equal to BP is 4H WH over square root of 5, and NP is, let me write it down. So this is MP. From my sketch here, I have VP equals 2WH times this, so I got 4WH over square root of 5, and I have NP equals 2WH over square root of 5. Yeah, okay, so that's fine, that's correct. Okay, so we have our P results and we have our 1 results. Now, what it was, the point I want to make is I saved myself the trouble of calculating the reactions, right? And what else? And when I take the free body of the bubble that is bigger cut in here, it's kind of easier to just look at that bubble than from here because you don't have anything at the beginning and so on. Anyway, it's a question of preference. I would certainly always do it like this in this case. Now, once we have that, we can certainly write our integrals and get what we want. Now, the reason why I kept bending was just to show you if we have this and I just keep bending, let's compare it with that one. Okay? So if I keep only bending, I'm going to have to erase something to create a little space. So I'm going to erase here. Okay? And then say, if we keep bending, to show. So we have delta C in the vertical direction in this new version would be M1 MP is the integral of x, that's the M1. The NP was WX squared divided by 2, and then EI dx and this was from 0 to 2h, right? Now that's just the same as before, because nothing changed on bar BC, right? What changes now is that the second bar is different, because now the second bar is the moment m1 still just x, right? And the moment mp is this one, which is 2whx minus 2wh squared divided by EI, and then here is the point, okay? Is not dx, because x is not running along this bar. X is a horizontal coordinate, and what goes here is ds, which is something that has to be running with the bar, all right? So now, if you look at that bar, this is in the direction of the bar, that's ds. This is dx, right? This would be dy in these coordinates. That bar, from similar triangles, is 2 to 1 to square root of 5, right? Therefore, ds is to dx as square root of 5 is to 2. And therefore, ds is equal to square root of 5 divided by 2 dx. So what goes here in this integral is not dx, is ds. And what is ds? Square root of 5 divided by 2 dx. That's it. That's the thing you have to keep in mind if you're integrating and your coordinate is not really in the direction of the bar. Now, what are the limits in this case? We're integrating in x, and for this bar to be covered, we have to start at 2h and we have to finish at 4h. And that's it. Notice that in this version, of course, the other time I was explaining things more slowly and doing it more slowly, but if you go over it yourself and you put it in clean in a piece of paper, you will see that with this alternative, the free body diagrams are cleaner, well, not cleaner, easier perhaps. The integration is, the expressions are shorter. So what's the disadvantage? None. Well, maybe one. You have to have confidence in what you're doing. You have to understand what you're doing, because you're doing something slightly off from the middle of the road, which is you're using a coordinate x and you're integrating along a bar that is not in x, right? Okay. Now, if you plug it in, into this case, we get that thing over there. And I actually checked it. So if you take this one, I'm going to leave that for you because it takes 1, 2, 3, 4 lines, 1, 2, 3, 4 lines of writing to solve, to do that. But when you do that, you find that the answer to this is delta C vertical is equal to 38/3 of WH4 divided times square root of 5 over EI. Okay? If you take this one over here and you do the integration, so, oh wait, I'm sorry, that's not true. That's not true, that's not delta C vertical. What I did was this, to keep things smaller. What I said was, this part here is obviously the same as this part here. So I did not calculate that part. I was trying to simplify things as much as possible to show that the answer is the same. So what I mean really is this integral is equal to 38 WH to the 4th over square root of 5 I mean 38 thirds of WH to the fourth times square root of 5 divided by EI. And this integral, which is the integral over that bar on the second way to do it, can also be computed, and you can confirm that it is, as expected, the same. So you can convince yourself, do this integral, calculate how much it is, you should get 38 thirds square root of 5 over EI, WH fourth, which is the same as this part here. Okay? And thus everything checks. Let's see. Okay. So having that, let's take a look at okay, so the next step is, well, not next step, but let's just do one very last thing that I thought from my experience maybe might be useful for you guys to look at. Let's say that the question was, on this same problem, calculate the rotation at B. Okay, calculate the rotation at B, including everything, axial shear and moment. Of course, due to what? Due to the same thing, right? The structural load remains the same. A uniform load here, W. So if the question is calculate the rotation at B, what you would do first would be to apply a oops, got wet still, and it doesn't work. So 1 kip-foot moment is applied there, so this becomes your new unit load, this remains your P load. Now, the P makes no difference, right? We could use it with Z, we could use it with just X, whatever. We've done it. We just have a new unit load case, because the question was what is the rotation at B. Now, from a free body diagram of the bubbles that start from this edge here, we conclude that M1 is 0, V1 is 0, and N1 is 0 for this bar BC, right? From a bubble that cuts from this end to here anywhere, we conclude that the moment here, M1, I have to be careful with the sign convention, that's the only thing. So when I take that moment, my sign convention with the MP, when I do this cut, was like this, right? Therefore, I find that in this case, 1 clockwise, 1 counterclockwise, so my moment is 1, my shear is 0, and my axial is 0. So this is the unit loading for 1 kip-foot moment applied at B. Okay? Therefore, theta at B would be the integral from nothing on this bar, right? And then, depending on whether we want to use Z or X, we could say, for example, using Z would be the integral from 0 to square root of 5h of our moment that used to be 6WH squared minus 4WH Z over square root of 5. That was our MP over EI multiplied times our M1, which is just 1. We're integrating in this case with Z, so that's just directly dZ, right? And if you do that integral, it comes out to be a couple of parts, but it turns out to be 4w h cubed square root of 5 divided by EI. Okay? Now, if you used the alternative, this is using Z. If you were using X, you would get theta B is the integral from 2h to 4h, right? Because now we're using X, and it would be the moment MP, which was 2w h x minus 2w h squared divided by EI multiplied by the moment M1, which is still the same 1, multiplied times what? Not times dx, but times ds, which is the square root of 5 divided by 2 dx. You can perform that integral and you get 4w h cubed square root of 5 divided by EI, which I did and checks perfectly fine, as it must, right? So that's it. I will review how much practice have you had with this thing when calculating these deflections. It is essential that you be comfortable with this material. It's very, very important, and I'll check with Ishmael, see what he's assigned, what he's come up with you guys for homework, and if it's not enough, then we'll add some more. In the meantime, while you're hunkering down, you can certainly apply the technique to calculate things that you know the answer to. That'll give you confidence, like previous problems that we did with double integration, that you know what the answer is. You can just calculate that deflection using virtual work, and so on, right? As much practice as you can, it won't hurt you. It certainly will help. So the next thing in the lecture today, and what we'll conclude it, is we're going to now extend our capabilities to the computation of deformations due to temperature. Okay, we're going to now consider deformations due to temperature. I'm going to erase, and again, in order to keep the files short, I'm going to stop here and start again. Okay.